The following program is video supplemental instruction. VSI is brought to you by the Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.
So I'm going to work through problem number 11 for Physics 2020 Midterm Exam 1. And in this problem, it says that a car starting from rest rolls down a hill. Assume there is no friction, and the speed at the bottom of the hill is 12 meters per second. And it's asking you, how high is the hill? And so I've drawn a little illustration here of the problem statement. And so we've got a car that's starting on top of a hill, and the initial velocity we can say is 0 because the car is starting from rest. And when the car reaches the bottom of the hill, the velocity is going to equal to 12 meters per second. And just as always, we want to set up our coordinate system. So this will be the positive y direction, this will be the positive x direction. And so we're trying to basically determine the height of the hill. All right, so the approach in this problem, we need to think about the information that's given to us. And one thing that we know is that when something is moving from a higher elevation to a lower elevation, or something is moving period, energy is always conserved, okay? And so if we keep that in mind, we can then go to our formula sheet that's given to us here for this particular exam. And if we look on our formula sheet, we can look at the section for the where it says conservation of energy. And basically, if we know that we know that energy is conserved, that means that the change in energy is equal to 0. Remember, energy can be converted to one form or another, but in a closed system, energy is always conserved, meaning that there's no net creation or destruction of energy. So the change in energy is always equal to 0. All right, so given this information, the change in energy then would be defined as your kinetic energy plus your potential energy, all right? And this would be the final kinetic energy and the final potential energy minus your initial kinetic energy plus your initial potential energy, okay? So that is your change in energy. And we know that this is going to equal to 0 since it's going to be conserved, energy is conserved. So basically what that means is that your final energy is going to equal your initial energy, okay? So knowing that your kinetic energy plus your final potential energy is going to equal to your initial kinetic energy plus your initial potential energy. All right? Now, given this information, we know that kinetic energy is equal to 1/2 mv squared, and this is your linear kinetic energy, okay? And that's given on your formula sheet under the conservation of energy section. And we know that potential energy is equal to the mass of the object times the speed of gravity times the height, the vertical height, okay? And so given this information, we can substitute this now into our equation, where we have 1/2 the mass of the object times the velocity of the object, and this is the final, okay? So this is final plus your initial potential energy, your final potential energy is equal to your initial kinetic energy plus your initial potential energy. Okay? And so this is our equation, and now we go to our problem statement and look at the information that was given. And we know initially that our height, we have some given height, okay? But our final height, we know, is going to be 0 if we assume that the coordinate system is in this way, okay? So our final height is 0, so that's going to make this whole term go to 0, all right? And we know that our initial velocity is also 0, okay? So that's going to make this whole term go to 0. So basically what we're left with is your final kinetic energy, right, is equal to your initial potential energy. Okay, so basically what's happening is all of your potential energy that you have is being transferred to kinetic energy when the car reaches the bottom of the hill. All right, so that's what this statement is saying. Now, given this new equation, the simplified equation, we know that the mass of the object doesn't change, and we see it on both sides of the equation, so that cancels out. So we're left with 1/2 times the final velocity is equal to gravity times your initial height. All right? And since we want to solve this equation for the height, we know that the height is going to equal to 1/2 times your final velocity over the speed of over gravity. So we now substitute in the information, so we get 1/2 times the velocity, which is 12 meters per second squared, divided by 9.8 meters per second squared, okay? And what happens is you'll have a meters cancel out with one of these meters, since this is a meter squared, and then the second squares will cancel out. We're just left with meters on top, okay? And that's exactly the units that we need for height. And when we plug in that when we calculate this, you're actually going to get 7.3 meters. All right, so this is how you would solve the problem. And basically all it is a transfer of potential energy to kinetic energy. And given that information, we know that the conservation of energy doesn't change. So that allows us to set this equal to 0. And because the initial height was, the initial velocity was 0, we canceled out this term. And the final height was 0, we were able to cancel out this term. That simplified our equation, which basically confirmed the fact that all of the potential energy was converted to kinetic energy. And then we solve for the height, and we've got an answer of 7.3 meters.
The Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.